This is a screencast on scientific notation, how to write numbers in science in the proper scientific notation. All right, so scientific notation, what is it for? Scientific notation is basically a shorthand that helps us more reasonably express very large or very small numbers so that we can kind of save ink and save paper and not have to write humongous millions of zeros across the page. It also helps us, we'll see, communicate how many significant figures or significant digits we confidently know in a number. But I'll give you more on that in a subsequent screencast. So, for example, what does scientific notation look like? So, let's say we want to talk about the speed of light. Okay, so the speed of light is roughly, because we do know it a little bit more precise than this, but it's about 3.0 times 10 to the 8 meters per second, okay? And this is written in scientific notation. What are the hallmarks of scientific notation? What are some features about it? Well, here, first of all, you see the opening number is a number between 1 and 10. So this is always written as a number between 1 and 10, all right? So your opening number needs to be in that format. If it's smaller than 1, you move the decimal place to make it larger than 1, and if it's larger than 10, you move the decimal place back to make it smaller than 10, okay? Also accompanying that opening number between 1 and 10, we then have like an order of magnitude, okay? So this will be an order of magnitude, which is a fancy way of saying it's 10 to the power something or other, or it's telling you how many zeros need to go before or after that opening number to make your actual value. Okay, so you can see that if we were to write this out in its full form, okay, we'd have 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then we'd have to put meters per second. So, what is the actual number? Well, it's 300 million meters per second, but hopefully, see, it's a little bit cleaner to just go ahead and write it in the standard scientific notation as aforementioned. Let's do a couple more examples. One thing that comes to mind for me is, you might wonder, what is the population of, what's a country with a big population? What's the population of Indonesia? Indonesia, I think, is Indonesia, I think, is the third most populated country in the world. It's not a geography lesson, but I think that's right. If you look it up, if you Google it, Google is going to tell you that, well, we don't really have a super accurate number for 2024, but it tells you something like there was 275.5 million people there last time we checked. Last time they tried to run a census and count, which was 2022. So how much do you think is there in 2024? Well, see, now we're estimating. We don't know exactly, right? Let's say there's maybe around, populations grow. Let's say there's around 300 million by now. Maybe that's a bit high, but let's take a crack at it. So let's express this in scientific notation. In scientific notation, 300 million means 300 with 6 more zeros attached to it. So, lo and behold, look at that. It's actually the same value, same scalar value as we had for the speed of light, 3.0 times 10 to the 8. Okay, that would represent 300 million, in this case, people. So the units are clearly different. How about a different country? What about India? We know they have a huge population. What is the population of India? And again, you can, that's ugly. Again, you can Google this, and they do have some more recent statistics, but it's going to kind of work towards what I'm aiming at. They say they have about 1.45 billion people, okay? What are they saying? They're saying we don't accurately know, just like they didn't accurately know in Indonesia beyond the 0.5 million. They don't really accurately know in India beyond the the 0.45 billion. They can't count every single person being born or dying on any given day. It's really difficult. So we only have a certain precision in that number, and we'll talk more about uncertainty and precision in subsequent lessons as well. But how would we represent a number like 1.45 billion? Let me show you this way. So, 1.45 billion, if we write the whole thing out, I think is like that, right? So in scientific notation, we would write 1.45 times 10 to the, how many spaces did we move it? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.45 times 10 to the 9 people, that's roughly the population of India in 2024, written in scientific notation. Check again. The very first opening number in this case is between 1 and 10. And then we put a power up there in order of magnitude to help us save ink, communicate clearly, and really demonstrate the figures that we know for sure, okay? Because in this one, we don't really know these figures for sure. They're all question marks. So, we don't want to write those down anyways. It's a little ambiguous if we know there's exactly 1,450,000,000 people, or if we just don't know. So we don't write them. That's a better, more clear way to communicate this in science. Here's one more. Why not? Okay, why not get a real sciencey one? So if we can look at bond lengths. Okay, so you may have done some structure and bonding stuff before. There's a little N triple bond. So if you look at that bond, okay, that bond length, if you look it up in a table of values, it says it's about 110 picometers in length. Okay, so the N triple bond length is 110 picometers. Can we write this in meters? Okay, so we're going to do a unit conversion. And I'll give you that. It's there's 10 to the minus 12 meters in a picometer. Okay, so this is a conversion factor of 10 to the minus 12. It's a standard metric SI conversion, but the picometer is very, very small. So what if we want to write this in scientific notation? We're going to have to, right? Because really, I'll show you why it's going to make much more sense to write this in scientific notation. So if we take 110 picometers and we're going to multiply it by that conversion factor, 10 to the minus 12, okay, and we're going to get our result is going to be 110, get rid of the picometer, it's gone. Gone. It's 110 times 10 to the minus 12 meters. Well, first of all, we only have 3 significant figures in this question, so that's aligned with that, but more on that later. But what else do you notice about this number that means it is not actually in proper scientific notation? Well, if you look at the number out front, it's not a number between 1 and 10. That number has to be between 1 and 10, which means we have to actually move that decimal place from here over to here, 2 spaces, okay? So writing this in proper scientific notation is going to be 1.10 times. So what's the move? By moving it 2 to the left, we made the number smaller. So when you make the opening number smaller, you have to remember to make the power of 10 larger by the same magnitude. Okay, so we moved it 2 spots. We're going to make the power of 10 larger by 2 orders of magnitude, and that is the proper length of the nitrogen triple bond in meters written in scientific notation. Don't forget or don't miss the fact that when you go from 10 to the minus 12 to 10 to the minus 10, the number got bigger. Okay, so if you move the decimal smaller, you make the order of magnitude larger.